But nevertheless, this is Introduction to Astronomy, and it's the outer solar system. And so let's begin with that. Now, much as we had a roll call of the inner solar system last week, let's do the same here. We have the four giant planets. Sometimes we refer to Jupiter and Saturn as giant planets, and sometimes we refer to the next two, Uranus and Neptune, as giant planets or as ice giants. So we sometimes call them gas giants and ice giants to distinguish between the two pairs. But there's a lot more going on in the outer solar system. There's dwarf planets such as Pluto, and others that have been newly discovered and, if anything, led to the reclassification of Pluto, and an absolute host of moons orbiting around the giants and various other interesting objects, which we'll have a little look at as well. So the scale of it is truly vast. We looked last time at the inner solar system and out just to the edge, to the asteroid belt, which is represented in the center here, occupying a tiny area by comparison to the orbit of the four giants, and indeed I've included Pluto on here. You can already see something odd about Pluto. Its orbit is highly elliptical, and it crosses inner to the orbit of Neptune and back out again. And that crossing in and out is really quite an interesting aspect of the story as to where Pluto might have come from. Now, last time we covered the asteroid belt, so I won't say too much about these. We had a look at a couple of the main members, but this is really the dividing line between the inner solar system and the outer solar system, in between the orbits of Mars and Jupiter. And I talked last time about the Titus-Bode law, where there was a gap in the numerical sequence that seemed to indicate that there was an object missing. And even when the planet Uranus was found, that too fitted into the scheme. And it's always good when a scientific idea can make a future prediction and then be confirmed right when the facts come in. And this Titus-Bode law worked for both the Uranus and for the discovery of Ceres in the asteroid belt. And Ceres was originally called Ceres Fernandina because the Fernandez, the king of Sicily, was a sponsor of Piazzi, and he was basically sucking up to his boss. Same thing actually happened almost with Uranus when that was discovered, which was that William Herschel wanted to call it Sidious Georgius, naming it after the King George that was on the throne at the time, in the hope perhaps of being awarded some money or even the role of royal astronomer. But after Ceres was discovered in that gap by Piazzi, the floodgates opened. Within the next year, Pallas was discovered, and then several more objects, all in that band that lies between Mars and Jupiter. You can see Ceres' orbit neatly fits in right in the middle of the gap there, just where the mathematical rule seemed to suggest it ought to be. That's all good. The orbit's a little bit on the tilted side compared to the flat plane of the solar system, and that indicates maybe that there's something a little bit unusual about Ceres, and that was true of most of the other asteroids as well. The best telescope picture of it taken from the ground was this one for many years, taken by, well, in fact, by Hubble, so taken from the Earth, the Earth's orbit. showing a mottled surface, not really any detail, but our space probes have been. The Dawn spacecraft has visited a couple of the asteroids in the asteroid belt, and it's currently in orbit around Ceres, and I think it's going to remain there. It hasn't got the fuel to do anything else. And it took this photograph as it approached of the soft cratered surface, and then this main crater in the middle here with these two white spots in the middle. And the white spots turned out to be ice volcanoes. Here's a flyby image that's been stitched together of an ice volcano bursting up through the ground on Ceres, showing that there is some sort of internal heat still generating geological activity on this interesting little dwarf planet, as Ceres was reclassified. In fact, when it was first discovered, it was deemed to be a planet, and then it got downgraded to be an asteroid. Now it's been upgraded to being a dwarf planet again. If we look at the spots in the middle of the crater, the detailed flyby shots are just amazing. They show these ice volcanoes erupting up from beneath the surface. Lots of that fresh white material has been brought up, and there's a color shot there showing that some of it contains mostly white, some of it's got that sort of pink tinge to it, and we'll see that pink tinge again on photographs of other objects in a few minutes. But all of this suggests that Ceres is a small rocky core with a white water ice layer over the top of it, and then a dusty ice covered frozen coating on the surface. But that water ice layer could be contain enough pockets of liquid and enough of a heat source in the middle to stop it freezing, and that's really all you need, plus some organic material, and there seems to be plenty of that on Ceres, to brew up the conditions for life. So it's a very, very interesting development that this could be somewhere to go and look for primitive life underneath the ice. The Dawn spacecraft also visited Vesta and showed it to be almost a sphere. It's a little bit off round, and it has a huge crater in the southern region here, covering almost a quarter of the surface. This lump is the central mound, and the crater goes right around here. And that crater, the Rio Silva crater, was formed and by an impact, and the fragments from it were blasted off all around the inner solar system, and many, many of them have landed back here on Earth. And there's a special class of meteorites that we pick up on the Earth's surface that are known to come from this little world of Vesta. That's about 40% in total of all the meteorites that you find on Earth come from this one event. In comparison, size-wise, the four largest, or three, well, here, I'll say it again, here are four of the largest asteroids in comparison, though, to our moon, which shows really they are quite small, because the moon is quite small compared to the planet Earth. It was soon discovered, though, that there are hundreds of thousands of other objects orbiting around in this region, all much smaller, and many of them with very irregular shapes. There's a collection of them here, such as the sort of potato-shaped Ida with its little moon, Dactyl, that orbits around it, Gaspara, Eros here, named after Anne Frank, Itokawa, that one's been visited by a spacecraft as well. And then these guys down here that have this other type of designation with a number P and then the name on the front. These are not asteroids, but the nuclei of comets, the frozen snowball that's the core of a comet. And they look very similar to asteroids. In fact, it may just be that the cometary versions are in much longer elliptical orbits and have a lot more water and volatile materials left in them because they haven't spent as much of their time near the sun. But when they do, that material gets boiled away to form the tails that we see in the sky. Anyway, let's have a look at the giant planets. So here's a picture of Jupiter. It's 10 times the diameter of the Earth, and being 10 times in each of the 3 axes, that means that you could drop 1,000 Earths inside it, but it's only 300 times the mass, so relatively less dense, only just slightly more dense than water, in fact. Its mass adds up to the vast majority of the material that is not part of the sun, though. It's 2.5 times the mass of all the other planets and moons all added together. So very much the dominant object in the solar system apart from the sun. And it orbits round the sun at 5 times the Earth-Sun distance, the astronomical unit, or AU, and it does that every 12 years, as you can see. Here's a fantastic picture of the cloud tops. We really can't see deep inside the planet to find out what's going on, although we did drop the Galileo space probe in there and learned a certain amount about what happens in the upper layers of these clouds, at least. So we know the composition, mostly hydrogen, some helium, much as most of the stars are made of the same material, with traces of other elements and other molecules there. So we've got the gases, methane and ethane, quite a lot of water, ammonia, hydrogen sulfide, phosphine, benzene, all sorts of things. They think the red spot here, giant red spot, is a hurricane. It's been raging since Galileo first looked at Jupiter. I've got a little animation of that. You can see we've held the great red spot almost stationary, and you can see how the rest of the atmosphere moves in quite amazing turbulent ways. See lots of little hurricanes coming along and encountering the great red spot. Most of them just get swallowed up into it. It's quite impressive. But it's about 3 times the size of the Earth. And what's happening is we're being able to see down into other layers of material at other altitudes in the eye of the storm. And the red material is mostly formed by the atmosphere getting sunburnt. It's the action of ultraviolet light on the molecules and chemicals in the atmosphere that makes them react with each other and form some of these brown and red materials, these so-called tholins, the same sorts of chemicals that we saw in that ice volcano at Ceres, and we'll see them again. The animation at the bottom there again just shows how the if you keep the red spot centered, then the rest of the atmosphere just seems to move around it. And this was taken by one of the spacecraft as it approached Jupiter. We can guess and estimate about what's going on in the center based on the density and our knowledge of science and some of the other measurements to do with magnetic fields and so forth. And what we find is that there's probably a small rocky core right in the center, a bit like a sort of giant version of the Earth. And then overlaying that, there's a very large and deep and pressurized layer of metallic hydrogen. This would be a liquid metal composed of the atomic form of hydrogen, where it's been squeezed together so much that all of the electrons become shared between all the atoms, much as this is the behavior of metals that we know around us. So a very highly electrically conducting layer, and that gives Jupiter an absolutely enormous magnetic field due to the fact it's spinning round on its axis once every 10.5 hours, even though it's 10 times the size of our planet. It whips round in half the time, and that stirs up a huge amount of electrical activity in the metallic hydrogen layer, very strong magnetic field, and interactions with the solar wind create the aurora, the northern lights and the southern lights around the poles of Jupiter. Only on Jupiter they are blue rather than the green color, as the ionized radiation hits the atmosphere. It makes the methane in the atmosphere glow with this blue color, whereas on Earth it's the oxygen in our atmosphere that tends to react and gives us the green of the aurora. Now, of course, Jupiter is accompanied by a family of moons. I can't remember the latest number. I think it's got up to 83 in total, but they keep finding new ones, so that number changes each time I give the course. It has, however, got 4 very spectacular large planet-sized moons that were seen by Galileo. You can see a page from Galileo's notebook here where he shows the disk of Jupiter and the little tiny specks around it that are the 4 large moons: Io, Europa, Ganymede and Callisto, that orbit around Jupiter. That's what they look like with a small telescope. You can usually see the bands across the equator of Jupiter, and the moons orbit around in that equatorial plane. Close up, though, from space probes, we get some magnificent views of the 4 Galilean moons, Io, Europa, Ganymede, Callisto across the top there, with zoomed in fragments of each of them underneath. So these are the grooves in the ice crust of Europa and so forth. Individually, this is Io. Looks like a pizza, but it's covered in sulfur, not cheese. And the different colors that you see on the surface there are the different colors that you get when you heat sulfur and cool it down at different rates. You get, if you cool it down very quickly, you get black, less quickly orange. Usually, if you cool fairly slowly, you get the yellow color that we're more familiar with. And if you cool it down really slowly indeed, then you get the white material. And so once you've excluded the colors of sulfur, there's not really very much left on Io there in that image. The reason for all this activity is it's the most volcanic place in the solar system. The core is boiling away. All the sulfur and other materials are coming up to the surface and bursting out. We can see a huge plume from an active volcano on the surface of Io here. There's another one there. There's another one there going off. Another one here. And here's another eruption just caught into the backlit backscatter of the light from the sun there. So you can see it churning away and producing these volcanic eruptions all the time. Europa, somewhat calmer environment, an ice covering with huge long grooves and cracks in it. Not very many impact craters. There's one there. That tells us that this is a surface that is constantly undergoing change and being covered over and resurfaced. Otherwise, the number of craters gradually accumulates. But all of this material here, the brown material, again, this is those organic molecules called tholins that have been formed photochemically, probably. So there may well have been organic material come up from underneath through the cracks in the ice. from a liquid ocean beneath, and then photochemically changed into these orangey brown coloured materials, or they were formed like that underneath and they've been brought to the surface. But either way, this again is a pointer to the fact there's a lot of organic material in that ocean underneath the ice. And Europa is probably the #1 candidate for discovering independently formed biosphere of life in the ocean, in that protected zone, protected from the ravages of the radiation from the sun by a very thick layer of ice over it. Ganymede, next one out, is the largest moon in the solar system. It's actually a whopper. It's bigger than Mercury. So if it orbited the sun, we'd have no trouble really calling this a planet, I think. And it too has ice and water layers within it. We're less sure whether they're fully melted or liquid layers or frozen up or some sort of slushy combination. Now, the reason that these moons are not dead frozen objects is all contained in this little diagram at the bottom here, which shows how the orbits are linked together. If you watch the innermost moon there, Io, zipping around, try and get my timing right, it's going to catch Europa at the top there, and again there, and again there. And so it's catching Europa, and you see it's every other time. On that occasion it caught it, next time there's nobody home. So it's a 2-to-1 relationship. And the same thing happens if you watch the second moon out, Europa. It meets Ganymede at the bottom there, goes round, nobody home. Second time round, it meets Ganymede again. And so they're in a 1 to 2 to 4 relationship. This pumps their orbits into being elliptical, which means they change their distance regularly between themselves and Jupiter. And that creates a tidal gravitational effect that stretches them into more rugby ball shapes. And then as they move further away from Jupiter, it releases its grip and they return to their natural spherical shape. And that squishing and stretching that they undergo is what provides the internal heat source that keeps them from being completely dead and frozen up geologically. The fourth of the Galilean moons, Callisto, is not playing this game. It's orbiting further out, but it's not in the same sort of integer relationship. And so its orbit is very circular. It's not getting very much internal heat generated by this tidal stretching. So it's solidified and all cooled down now, and accumulating more and more craters on the surface. So we see an old crater covered surface on Callisto, much as we do on our moon. Now, Jupiter also has a system of rings. In fact, the Voyager probe revealed that all of the outer planets have a system of rings, not just Saturn. Only Saturn's are by far the most comprehensive. So Jupiter's got its own rings around it. And of course, it has lots of other lesser moons, moonlets, including things like Amalthea here, which is the next largest, that orbit around in the ring zone and control the position at which the rings form. There's a picture of Amalthea here. We've not actually been close enough to it other than to be able to see this and see that it's clearly far from round. That's because it's too small. Anything over a few hundred kilometers and gravity starts to be able to force the rock into the spherical shape so that it's has the minimum energy configuration, something that Isaac Newton proved. And around Jupiter, there are all the rest of the irregular moons, all orbiting in a complete bird's nest around it. As you can see here, some of them go the right way round, as in the same direction that all the planets orbit the sun. Others go backwards. That's chaos, as you can see from that diagram. But Jupiter also controls the asteroid belt. Not only does its gravity corral the limits of the main belt, but there are some asteroids that are trapped in Jupiter's orbit, positions called the Lagrange points. They're 60 degrees ahead of Jupiter and 60 degrees behind Jupiter in its orbit. And these are relatively stable. Sorry, I've got a little animation that shows actually the main belt asteroids that we think of as in that circular belt around the sun between Mars and Jupiter. But Jupiter's gravity interacting with that of the sun puts each individual asteroid into an elliptical orbit, but collectively they form this weird, slightly curved triangular geometry, where the points of the orbits that are furthest away from the sun come out and meet Jupiter's orbit at one of three places. And if they meet at the Lagrange points, there's a chance the asteroids get trapped there for a while and become part of the group that just stay out in Jupiter's orbit there, the ones that are marked in green. These are all real orbits of the real asteroids, the largest ones. Quite amazing to see how it's really not quite the structure you naturally would expect. And the other effect that Jupiter has is to force the asteroids into this geometry, where some ratios of the orbital period, the time taken to do an orbit, are highly unfavorable. So, for example, we have anywhere from 2.1 astronomical units just beyond Mars out to 3.5 here on this graph. And we've plotted the number of asteroids at each position. And you can see that here at 2.5, that's a 3-to-1 ratio with Jupiter's orbit in terms of the year length. And that's not stable. Any asteroid that tries to get into this orbit soon gets kicked out of it. And there are others at 5-to-2 and 7-to-3 and 2-to-1 particularly that are bad orbits to try and adopt. The others are much more popular, and that's because these can be stable, whereas these you persistently get a kick in one direction from Jupiter and it knocks you out of that orbit quite quickly. Moving on out to Saturn, we find a slightly smaller planet than Jupiter. It's still actually, without its rings, it's 8.5 times the size of Earth. So it's not far behind Jupiter. But with the rings, it's actually covers a greater radius. Anyway, you can see the basic numbers there. I won't read them all out. This 29.5 years for the period that it takes to orbit the sun is in a 5-to-2 integer relationship with Jupiter. And the two control each other to a certain extent. Over a period of 1,000 years, they gradually nudge each other into longer and shorter orbits and oscillate. Magnificent shot there taken by the Cassini space probe of the planet with the rings and showing the gaps in the rings. Those gaps in the rings are just like the gaps in the asteroid belt, and they occur because the large moons of Saturn are interacting gravitationally with the ring particles to kick them out of the orbits that lie within this gap, the Cassini division, and again this narrower gap here called the NK division. If we look at Saturn, courtesy of some of the images from the Cassini mission, it discovered again the blue aurora, telling us that Saturn has methane in its atmosphere and a very strong magnetic field to whip the solar wind up and focus it down on the poles and create these northern and southern lights. And rather surprisingly, the wind patterns have managed to form a quasi-stable hexagon arrangement. So the polar hexagon sits on the pole of Saturn, and really it's a number of hurricanes that are orbiting around, 6 of them, round one central one. And it turns out you can pack 6 rotating hurricanes round a central one in a nice, stable and efficient way. Not so easy to do it with either 5 or 7. They end up interfering and destroying each other. But 6, you can get a very stable wind pattern. Here's a backlit picture of Saturn with its rings that was taken with the sun in hiding behind. So the Cassini probe went into the shadow of Saturn to take this picture, and you can see the complex structure within the rings. There's not just the 2 gaps, but there are many thicker and thinner patches to the rings, and even some outer rings out here containing much more sort of dusty material that you wouldn't normally see. But I'll draw your attention to this little dot here. That's you. That's the little blue dot. That's the Earth being seen through the rings of Saturn by the Cassini space probe. So everyone who's alive or has ever lived is on that little blue dot there. And I think that's quite a sobering thought. Now, the greater and lesser moons of Saturn are all, as I said, responsible for organizing the patterns within the rings. Here's a good example. There are 2 little moonlets called Pandora and Prometheus that act to shepherd all the particles in the F ring here and keep it in its nice tidy orientation. They also create these weird striations and spokes as they go around and approach the rings. So the gravity creates quite a lot of interesting substructures in the rings. And here on the outer edge of this ring, we think there's a new moonlet being formed out of the dusty material. You can see the little blob on the end of a sort of dead end bit of ring. We think that's a moon gradually being created. The largest moon of Saturn is Triton. It's nearly the same size as the planet Mercury, and a fascinating world in its own right. It has an atmosphere that's 50% more dense than that of the Earth, and full of dirty, dusty smog, so that we can't see down through it with ordinary telescopes. So when NASA sent the Cassini probe to Saturn, the European Space Agency hitched a ride on it with their Huygens lander, which parachuted down through the atmosphere of Titan and discovered scenes like this big picture at the bottom here, with mountain ranges rising up from the floor. It's a little bit fisheye distorted because of the way the camera worked, but with these long valleys in between. And on the valley floors, there are what look like rivers, braided river channels running across the surface. It landed and sent this picture back of this orange landscape with lots of round rocks, round pebbles that look like they're on a beach. And it probably was either a dried up riverbed or a beach that it landed on. We're not quite sure. Next time they're going to send a rover of some sort. But they also used the radar on the lander to image down through the clouds and discover lakes such as this one, the Kraken Mare. And you can see how the river channels are meandering and braiding and getting together, merging, and then outflowing into the lake. And so this lake is part of the liquid cycle, but it's liquid methane. The temperature on Titan, minus 160 degrees C, it's too cold for liquid water to exist. So this sort of, all of the river contents and lake contents and the clouds are all substituted with methane, natural gas, as we would call it on Earth. Here's an example. We've got clouds of methane forming and moving across the surface, and then presumably raining out, because this little lake has gone from near dried up to refilled. And we see that with the giant lake Kraken Mare as well. If we look at this area of this little peninsula over different flybys, you can see the shape of the land has changed. And in fact, it's changed in a way that's consistent with the level of the lake overall, having gone up and down. More cloud features, again, released just the other day by NASA. So still getting some pictures through. And the real star of the show at Saturn was the little moon Enceladus, only 500 kilometers across, but nevertheless another of these snowball worlds, these ice worlds, where there's an ice covering that's refreshing itself, so it's not picking up too many new craters. What craters it does pick up are getting destroyed by geological processes. But huge cracks in the ice called the tiger stripes, these blue cracks here, and they're venting material out into space. This is a backlit shot over one of the tiger stripes, showing a plume of material leaking out into space, and a false color picture of the same thing. And they flew the space probe through the plume and discovered that it was water, and it contained a mixture of organic chemicals and some molecular hydrogen, just H2. And that's quite unusual to find organic chemicals and hydrogen present like that in a mixture, and is suggestive of some sort of biological activity again in this liquid ocean over the rocky core of Enceladus. Other moons of Saturn have all sorts of interesting properties. I don't have time to go through all of them, but this is Iapetus, that has this equatorial ridge along its middle here. You can see it going right around the moon here. Nobody knows how that's formed. Some people say it might be a captured asteroid that was shredded and deposited all its material, or maybe it was a ring around Uranus, not Uranus, Iapetus, that condensed onto the surface. Some people have said it's where they've glued the two halves together, but I think that's perhaps more fanciful. Lots to say about the rest of the moons of Saturn. There are other ice worlds there. There are all sorts of amazing things to look at, but we have to move on. And this is the picture of Uranus, showing that size. It's 4 times the diameter of the Earth, and therefore contains 4 times 4 times 4, which is 64 times the volume, but only 14 times the mass. So again, relatively less dense than a typical rocky planet. That's because it has this huge envelope of gas and volatile materials sitting on top of it. 1 or 2 little features in the cloud belts here, but otherwise a rather boring picture. Was bit of an anticlimax when that came through from Voyager 2, which is the only spacecraft to go out here this far from the sun. The planet was discovered by William Herschel. He was in the middle of studying double stars with his telescope from his back garden in Bath, thought he'd found a comet, reported it to the Royal Astronomical Society, but its orbit soon revealed that it was way beyond Saturn and orbiting it in a near circular orbit. So the first person in modern times to discover a planet. But it's a bit of an oddball in some ways because it's tipped right over on its side. And so the rotation can be such that the poles are pointing towards the sun and away from the sun, and that the planet is rolling along its orbit on its side at times, and at other times it can be rotating into and out of daylight with the poles pointing along a tangent to its orbit. It has rings, and it also has a family of moons that are quite fascinating. Again, we don't have time to go into too much of that. Its discovery soon led to the prediction and discovery of the next planet in the sequence. As I said earlier, William Herschel discovered Uranus optically with a telescope, wanted to call it Sidious Georgius after the King of England, but nobody would put up with that. So eventually sanity prevailed, and Uranus, the father of Saturn, in mythology seemed appropriate given its location. Well, its orbit didn't seem to quite add up, and John Couch Adams in Cambridge and Urbain Le Verrier in Paris independently went about solving the problem and predicted that there was another planet out beyond. And of course, eventually it was found, and Le Verrier's predictions were used to make the discovery. So he gets the lion's share of the credit on this one. And we call that planet Neptune, after the god of the sea. Very sensible. In this case, Le Verrier wanted to call it Le Verrier's planet, but nobody else was interested in that. And Neptune had been a suggestion for the name for the planet Uranus at one stage, until Uranus was widely adopted. So Neptune, slightly smaller in radius than Uranus, but slightly more massive. And it takes 165 years. The time taken to go round the sun increases quite dramatically as you move further away. The amazing Voyager 2 shot here with the great dark spot, a little bit similar to the great red spot on Jupiter, but the chemistry in the atmosphere is different. There's a lot more methane and a lot less hydrogen. And so the coloration is very blue. A real surprise was the large moon Triton that orbits Neptune. Again, it's a planet-sized moon. We got this one composite photograph from Voyager 2 of a flyby of Triton, where we were expecting, of course, a crater-covered surface, but not so. And the surface is amazingly young-looking and dynamic-looking with geological activity, hardly any impact craters at all. Up in the top here, it's called the Cantaloupe Terrain, named after the skin of a type of melon, and has these amazing grooves, reminiscent of the grooves that run on the surface of Europa, suggesting perhaps an ice-covered ocean of some form. Maybe not of liquid water at this case, though, because the temperature out this far from the sun is now down to a chilly minus 230 degrees centigrade. And then this hemisphere is all covered in this pink snow, which is frozen nitrogen. It's nitrogen snow. Nitrogen is the gas that is the lion's share of the air you're breathing right now. It's can be liquefied, and if you cool it enough down to these sorts of temperatures, it can be turned into a solid. And so it has snowed nitrogen onto the ground here. But the real feature is these black bits, these streaks, these that line up. They're all pointing the same way, and they're all pointing in the prevailing wind direction on Titan, downwind. And what we think they are these amazing geysers that are erupting from the subsurface, and they're probably liquid nitrogen that has melted and then tried to boil and burst through, much as geysers on the Earth made of superheated steam do the same thing. And they're bringing with them a lot of very dark material, which they deposit downwind. And we're not sure what that dark material is, or why it would be happening quite that way. But it's very interesting, again, from the chemistry and the chemistry of life point of view, to understand that wherever you have thermal processes generating activity and movement of a liquid, and you have a temperature gradient, that's enough usually for life to find it to be habitable and to give it all the things it needs to live on. So we need to study Triton some more. Now, interestingly, if we go back to that Titus Bode law and fill in the rest of the planets that we now know about, and we use Ceres in this gap here, it fits very nicely. We've calculated the Titus Bode distance, 2.8 for Ceres, and the real distance, 2.77. So it's only an 8% error. That's pretty good. In fact, it's better than the 5% error for Mars. As we go out, Saturn also 4.8%, Uranus even better, 2.8% error. Neptune, however, just does not fit. There's a 30% error, and you can see the Titus Bode law fits nicely all the way out here, but for Neptune, its prediction and the actuality just deviate horribly. And if you try and plug Pluto in as the next planet in the sequence, well, you're nearly 100% wrong. So it's just a terrible fit. So it could well be that the Titus Bode law is really just a numerical accident, in fact, and that there's no more science to it than that. But having discovered Uranus and then predicted and discovered Neptune, further perturbations in the orbits of the planets led to the suspicion that we hadn't found them all yet, and that there was a planet X out there. That led to Percival Lowell here building his Flagstaff Observatory and charging Clyde Tombaugh with doing a search for Pluto. It's the Discovery image pair are here. Even with the helpful arrow, it's still quite difficult to spot Pluto. But Clyde did spot it in 1930, and it was immediately thought to be a planet. People were expecting a substantial chunk, maybe as big as the Earth or even larger. Some people published articles suggesting it was larger even than Jupiter. But in 1978, we began to get some real hard science as to the size of Pluto, because its little moon Charon was discovered, and the photograph is here in black on white. The black is Pluto, and then here Charon is just poking out on the top here, and with the two orbiting each other, suddenly you can start to get a handle on things with mathematics and work out their masses and their size and so forth. Very much the case that Pluto is smaller than our moon, and Charon is quite a big moon in comparison to Pluto. As a result of the fact that one was passing in front of the other, they were able to use computers to synthesize a picture of what the surface of Pluto might look like. And you can see it's got this heart-shaped bright region, somewhat similar to the shape of Africa, that they thought ought to be there in the data as a result of the overall brightness changes when Charon was orbiting in front of and blocking the view to the surface of Pluto. Managed to unstitch all of the sort of overlaid light and come up with a model for what was causing it. Now, in fact, the estimates of the size of Pluto, here we have a little humorous graph actually, which showed that they were expecting a very large object, but as estimates kept on coming in, by the time they'd got to 1978 and the discovery of Charon, the estimate came down to 1/500th of the Earth's mass. And they even predicted that if this process carried on, it was going to disappear completely. But that was very much a tongue-in-cheek prediction. So because of its small size and because of its strange orbit, and because other objects were being discovered out beyond Neptune, it was decided that Pluto would be demoted to dwarf planet. And in fact, its small size meant it could never have been responsible for the believed errors in the orbits of the giant planets. And in 1992, some analysis of the Voyager spacecraft trajectory showed that we'd got the mass of Saturn wrong in our estimates by 0.5%. And if we plug that number back into all our calculations, then everything comes out right. And there's no need for a large missing planet X to be believed to be out there. And so Pluto was very much discovered on the basis of a bogus prediction due to a misestimated mass for Saturn. But NASA sent the flyby mission, the New Horizons spacecraft. It was already on its way when Pluto was demoted, and it did a flyby. It approached Pluto and immediately began to discover more moons in the system. So here is Pluto and Charon taken by the approaching spacecraft. It found a couple of small moons here as it approached, and they were called, they've been named Nix and Hydra. And then it's found two more, which have been called Styx and Kerberos. So quite a complicated little system in its own right, Pluto. But then the probe did a close flyby. It didn't have the fuel to slow down and stop. And it took this photograph of the surface, which shocked everybody because there is almost an absence of craters. And we really can't quite explain why Pluto does not have an ancient old surface covered in craters, because with its small size, it shouldn't have been able to trap enough internal heat to then continue its geological activity all the way to the present day. But it clearly is. This is a huge glacier that's moving across the surface of Pluto, rubbing out the impact craters. This one here is for the chop. The glacier is going to rub that out and fill it in and destroy the record of the impact ever having occurred. We've got a false color image of Pluto here, where the color of the surface has been enhanced based on the real color and the chemistry of the region. So we can label that up. The blue up here, that's frozen methane. This is red down here, that's ordinary water ice with a lot of these tholins in it again. We have frozen out nitrogen snow up the top there. And then the glacier, which is not made of water ice, but made of frozen up carbon monoxide, methane, and nitrogen mixed together. And it's marching its way across the surface. Here's another couple of shots of that glacier. A close-up shot here shows the structure. It looks very much like the sea ice on the Arctic regions. I've also discovered more of these ice volcanoes on Pluto, where these mountains have been identified as eruptions of ice from beneath. So a cryovolcano, low temperature volcano. And all of this activity just is still unexplained. We don't know why Pluto hasn't lost all of its internal heat. It certainly seems to have had time. More fascinating shots, a few impact craters on this region, but up here the glacier has been and swept over it and erased the record. Raw shots of Pluto looking back, catching the thin atmosphere by backscattering the light from the sun. So we can see that these amazing terrains with sort of dunes covering higher areas here. And one thing that they found was grooves in the ice with these dark features which seem to disappear down inside them as deep pits, and nobody really quite knows what is going on there. Even Charon, the moon of Pluto, is very interesting. It's got a few more craters on it than Pluto, but not very many, and very much a sort of moon of two halves, where there's a join or a raised platform around the middle here, and this hemisphere, the top hemisphere on the picture, is higher than the ground around the lower half for some reason. But we got absolutely fantastic images of it, so scientists can spend a lot of time going over this and trying to understand better what's going on here on this moon in the outer part of the solar system. Now, I said that there were other objects that had been discovered out beyond Neptune, other than Pluto, and they form a second asteroid belt called the Kuiper belt. We found hundreds of thousands of these, some plotted in green here on this diagram. There's Neptune, for example, so further out. And Pluto is just one of this population. The reason there's a gap there is not because there aren't any objects, but because we hadn't looked there. Here's some artist's impression of a few of them. Actually, we've got a real photograph of Pluto and its family of moonlets that it's acquired. But similar in size to Pluto is Eris, and it too has a moon, dysnomia. And it was really the discovery by Mike Brown in California of Eris that put the cat among the pigeons for Pluto, because if Pluto was a planet, then surely Eris needed to be, in which case what of Makemake and Kwame and some of these other guys that were being discovered out beyond Neptune, and we were going to end up with dozens of planets very shortly. So the Astronomical Union decided something had to be done. The organization of this second asteroid belt gets dictated by the gravity of Neptune, and so we have objects like Pluto that are in a 2 to 3 orbit around the sun compared to that of Neptune. So they do 2 laps for every 3 that Neptune does. Pluto is one of those, and the others are called Plutinos now. And then we have two Tinos, which are in a 1-to-2 relationship with Neptune, and other funny names. The Cubewanos here are named after the first of the objects to be found, which had the designation QB1, hence Cubewano, for those that were in the intervening range. Now, I've used up all my time for tonight, so I'm going to have to bring the story of the outer solar system to a close. But just to say, this is not the end of the solar system. There are more objects way out beyond the edge of the Kuiper belt in what's called the scattered disk. And we're finding more and more of those all the time. There's even a hint that there might be a decent sized planet waiting out in the scattered disk to be discovered, but a search has been organized and found nothing. So that's another story to be finalized at some stage. And then beyond the scattered disk is a huge sphere of leftover material, little dirty snowballs called the Oort cloud, which really is the limit of the sun's reach. And these are the home and the source of many of the long period comets that fall into the solar system. So with that, I'll bring the talk to a close, and I hope you've enjoyed this, the fourth part of our introduction